Lab 3, Black Hole Orbit. The purpose of this lab was to estimate the mass of a black hole given the position data, time step, and mass of a star orbiting that black hole. We were to assume that the net force on the star was solely due to a black hole at a given initial position. In order to do this, I created a computational model in PHYS using Newton's second law in the form of the momentum principle and the universal law of gravitation, which estimated the mass of the black hole to be 1.99 times 10 to the 31st kilograms. In setting up the PHYS code, I initially told it to take the position data from a separate data file. Then, I added in the black hole in both the visualization and graph setup to be a black sphere, and in the initial system properties where we set the star's mass, black hole's initial position, and delta t to the given values in the problem. From the given position points, PHYS is able to calculate the change in position over change in time on each time step, equaling the change in velocity on that time step for both the x and y components. If we multiply this by the star's given mass, this gives us the star's momentum for each time step, and dp over dt equals Fnet. This lab is different from the previous physics problems we have done because normally we are given the net force and initial conditions, and we use those to predict the motion future. Whereas in this lab, we are given all of the separate initial data components, in this case x and y position coordinates, and we use those to find the net force. We then use the momentum principle of P equals mv to compute the star's initial and final momentum vectors and change in velocity, vf minus vi, and change in momentum, pf minus pi. We then use Newton's second law in the form of the momentum principle to calculate Fnet in terms of its perpendicular and parallel components. We know that Fnet equals dp over dt, and p hat, the direction of dp over dt, is the initial momentum over the magnitude of the initial momentum. So then, the magnitude of dp over dt is the magnitude of p final minus the magnitude of p initial, all over delta t. We also know that because the only force acting on the star is the black hole, that Fnet parallel equals dp over dt parallel, and Fnet perpendicular equals dp over dt perpendicular. We know that dp over dt parallel is going to be the magnitude of dp over dt times p hat. Therefore, since dp over dt equals dp over dt perp plus dp over dt pair, then if we rearrange the equation, we can compute it so that dp over dt perpendicular equals dp over dt minus dp over dt parallel. So, we know that dp over dt perpendicular equals the change in momentum over the change in time, which is the info we have from the star's data that I showed earlier, minus the magnitude of p final minus the magnitude of p initial, all over delta t. Then, since the net force on the star is the gravitational force of the black hole on the star, we can use the universal law of gravitation, seen here on the left, to find the mass of the black hole. If we rearrange the equation to mass of black hole equals magnitude of Fnet over r divided by the constant g times the star's mass, then we will get an approximation of the black hole's mass if we tell PHYS to print black hole m. When I ran the code at first, I got the right approximation of the black hole's mass, but the picture was not incredibly accurate. I had to then go and change the window scale at the beginning of the code in order to be able to see the whole image. So now that we can see the whole image, the yellow arrow represents the direction of Fnet, which points virtually downward for the whole time, in the same direction as the black hole. The black arrow that represents Fnet parallel starts in the opposite direction of motion, meaning that the object is slowing down, and then points in the direction of motion, meaning that the object is speeding up. The blue arrow representing Fnet perpendicular points in the direction of the star's curvature, which is towards the black hole. What does it mean? So, Fnet and dp over dt have a unique relationship. Fnet equals the perpendicular component of Fnet plus the parallel component of Fnet. And we know that from Newton's second law, Fnet equals ma. dp over dt perpendicular equals the parallel component of dp over dt plus the perpendicular component of dp over dt. We also know from the momentum principle that dp over dt equals mass times change in velocity over change in time, which also equals ma. So therefore, Fnet equals dp over dt. Between the two is that when Fnet is what causes the changes in momentum. Speeding up or slowing down changes the momentum in the parallel direction caused by a force acting on the object. Curving changes the momentum in the perpendicular direction caused by a force acting on an object. In the case of this lab, the only force is the gravitational force of the black hole on the star, causing a change in momentum in the perpendicular direction. What if a new black hole with a new mass would change the net force acting on the star because F net equals g times mass of black hole times mass of star all over the distance between the two squared. This new net force would cause the star to orbit in a new motion with different perpendicular and parallel momentum that reflect the new gravitational force. If the mass of the black hole changed, then the gravitational force would change. And since the gravitational force is the only force acting on the star, the net force on the star would change, therefore changing the momentum and orbit of the star. In conclusion, using VPython to calculate the change in velocity and momentum over multiple time steps, and then plugging these into the momentum principle and universal law of gravitation to approximate the mass of the gravitational force, we were able to calculate the mass of the black hole.